Okay, so let's start talking about predicates and quantifiers. We're still on discrete mathematics. Now let's begin. Let's have a recap on the propositional logic. So we have the atomic propositions or the propositional variables. We can use P, Q, R, S, T, U, and so on. And we have the different Boolean operators or the logical connectives, the negation, the conjunction, that is junction, the XOR, we have the implication and the double implication or biconditional. And we have an example of compound propositions. So compound propositions are two or more propositions combined with these logical connectives. We have equivalences. That means the left side is simply equivalent to the right side. No, and we have proving equivalence using the truth tables and symbolic derivations or the laws, the De Morgan laws, and even the rules of inference. Now, what is a predicate logic? We have here a definition. A predicate logic is an extension of propositional logic. It permits concisely reasoning about the whole classes of entities. Like for examples of a class, we have an integer class, a student in CSC department, and etc. So let's proceed. What are the applications of predicate logic? A predicate logic is the formal notation for writing perfectly clear, concise, and unambiguous mathematical definitions, axioms, and theorems for any branch of mathematics. So it is one way to show a systematic solution or definition of anything that's related to math. Now, predicate logic can also be applied in statements like this. X is greater than 5. We all know that x is greater than 5 cannot be considered as a proposition because its truth value depends on the value of x. And in this case, we did not specify the value of x. Hence, we cannot consider this as a proposition. Now, predicate logic can be used to make this statement a proposition. That is by giving an exact value for x. For example, your P of x will be x is greater than 5 such that x is an element of real numbers. So we can substitute any value to x. Let's say x is 4. Then we can have P of 4 is simply equal to 4 greater than 5. This is a proposition and its truth value is false because 4 is less than 5. Now, a predicate logic can be used to make propositions from such statements, just like the example that I have just given. Now, let's continue. Let's distinguish subjects and predicate. So for this example, the dog is sleeping. The dog here is our subject, and the predicate here is modeled as the function or given by P of x, or x is sleeping, simply that one. Okay, so a predicate is a rule that assigns to each value in the domain whether it's true or false. So in the following pages, we will be able to dig more about predicates and propositional function. Now let's talk about more for predicates. We have the lowercase variables x, y, z. They denote the objects or the entities. And we have the uppercase variable. It denotes the propositional functions or the predicate. So the result of applying a predicate P to an object x is the proposition P of x, or simply the propositional function. Now the predicate P itself, for example, P is sleeping, is not a proposition. It's not a complete statement because we only have X, we only have is sleeping in here. But if we have here the subject, dog, and the predicate is sleeping, or we have the subject, the dog, as the subject, and is sleeping as the predicate, then we can now make a statement out of it. So let's say that X is your subject and P is your predicate. Combining these two, we will have P of X. Now let's talk about propositional functions. Predicate logic can also involve statements with more than one variable or argument. For example, let P of X, Y, and Z be the statement X gave Y the grade Z. Then, if X is Mike, Y is Mary, Z is A, substituting these to our statement, X gave Y the grade Z. So let's go ahead and write this one. Okay, X gave Y the grade Z. X is Mike, so we'll substitute Mike to X. Copy gave. Y is Mary, so let's substitute Mary to Y. Copy the grade, and we have Z is A. So this means that P of X, Y, and Z is simply the statement Mike gave Mary the grade A. Okay, so let's try the other example. Let Q of X, Y, and Z be the statement X plus Y is greater than Z. Then what is the truth value of Q of 1, 2, and 3? So the answer is false. We will find out why the answer is false. Now, given your statement is, maybe we should use black, okay, or a much bolder one. Given your statement X plus Y is greater than Z. So we'll be substituting 1 to X, 2 to Y, and 3 to Z. We have 1 plus 2 is greater than 3. 1 plus 2, that is 3. Copy the symbol and 3 in here. So this becomes false because we all know for a fact that 3 is not greater than 3. Instead, 3 is just equal to 3. Now let's try Q of 3 of 2 and 1. The given truth value here is true. So let's show why is it true. Given that X, let me erase this first. Given your statement, X plus Y is greater than Z. So 3 will be substituted to X. Copy the operation. 2 will be substituted to Y. Copy the symbol. And 1 will be substituted to Z. We have here. Now 3 plus 2, that is 5, greater than 1. So the truth value is true because it is a fact that 5 is greater than 1. That is the use of propositional functions in predicate logic. It will help us create propositions out of statements that do not have truth values. Okay, we have specific values for our variables in the propositional functions that will be or that will help us create or find out the truth values of those statements. Now let's talk about the universes of this course. A mathematical function may be valid for all values of a variable in a particular domain called the universe of discourse. Let's consider the example p of x is equal to x plus 1 greater than x. We can then say that for any number x, p of x is true. Instead of writing down 0 plus 1 is greater than 0, and 1 plus 1 is greater than 1, and 2 plus 1 is greater than 2. So this is more of a general form of your discourse. Okay, so let's talk about the different quantifier or the quantifier expressions. We have two, the universal and the existential. Let's begin with the universal quantifier. It's given by this symbol. Okay, if you have here this symbol, if you can see this symbol, it means p of x is true for all the values of x in the universe of discourse. Or you can simply say for all x, p of x is true. Or you can say for every x, p of x is true. That is for the universal quantifier. Next, we have the existential quantifier, and that is given by this symbol. Alright, if you can see this form, that means there exists an x in the universal discourse such that p of x is true. Or you can directly say that for some x, p of x is true. Or there exists an x where p of x is true, or there exists an x that makes p of x true. Take note, this symbol is for all or universal quantifier. This symbol is for existential quantifier. So this universal quantifier, all. Existential quantifier, there exist. Again, for the universal quantifier, to make it true, all of your values of x, once substituted to your statement, should be true. For the existential quantifier, you can only have at least one value of x that will make your statement true. Okay, so for all, or the universal quantifier, all values of x should make your statement true. For the existential quantifier, you can only spot at least one value of x that will make your statement true. Okay, let's have the universal quantifier. For example, let the universal discourse of x be the parking spaces at PU. Now let p of x be the predicate x is full. Then the universal quantification of p of x is given by for all x p of x. This will lead us to the proposition all parking spaces at PU are full, or you can also say every parking space at BU is full, or for each parking space at BU, that space is full. Now let's go back in here. Let's have an example for the universal quantifier. Again, for a universal or for this statement to be true, all your values of x that should be substituted to your statement should also be true. So let's have, for example, if I have here p of x is equal to x is greater than 3. We need to show that for all x, p of x is true, given that our domain or x is an element of real numbers. So any numbers that will be substituting to x, this will make the statement x greater than 3 to be true. So if x is 1, then we have here 1 is greater than 3. If x is 4, we have here 4 is greater than 3. If x is 5, we have here 5 is greater than 3. Now we have seen A value of x that disproves our statement 1 greater than 3 because 1 is less than 3. So this means that for all x, p of x is false. And this particular example is called a counter example. A counter example is something that you can see or a value of x that will make your statement false. Again, if makakita mo ing ani na symbol or ing ani na proposition, dapat tanan value ni x na imong i-substitute kan p of x true ang mugawas. If not, then that statement is false. And if you can see a value of x that will make it false, that is called a counter example. Now let's move. We have the existential quantifier given this symbol. For example, let the universal discourse of x be parking spaces at BU. Let p of x be the predicate x is full. Then your existential quantification of p of x is given by this symbol. Or in English sentence, we can have there is a parking space at BU that is full, or at least one parking space at BU is full, or some parking spaces at BU is full. Now, for the existential quantifier, you only have to spot at least one value of x that will make your statement true. Okay, for example, I have here, let's say let's say for some x, p of x is true. Now, we only need to find at least one value of x that will make p of x be true. Given that your p of x is the statement, let's say x plus 1 is greater than 3. So we can have, let's say if x is equal to 1, right? If x is equal to 1, x plus 3, x plus 1 rather, x plus 1 is greater than 3, then this will be 1 plus 1 is greater than 3, 2 is greater than 3. This is false. Let's say our x is equal to 3. So we'll have from x plus 1 greater than 3, we have 3 plus 1 greater than 3, 3 plus 1 that is 4 greater than 3. This is true. Take note that we use the existential quantifier. That means although the other value of x makes this statement false, we have found one value of x, or at least one value of x that makes it true, then that means the entire proposition quantified by the existential quantifier is true. So again, for the universal quantifier, dapat tanan values ni x na i-substitute nimo sa proposition, true ang mugawas for it to be true. For the existential quantifier, makakita lang ka na isa ka variable to be substituted to your proposition or to your statement that will be considered as true. And also, do not forget the counter example or a value of x that will disprove your proposition. Now let's continue. We have quantifier equivalence loss. So the definition of quantifier is given that our universal of discourse is given by A, B, and C. So for the equivalence loss, this means that the left side is simply equivalent to the right side. So in here, for all x, p of x is just equivalent to p of A and p of B and p of C and so on. Next, we have there exists x such that p of x is simply equivalent to p of A or p of B or p of C and so on. And we have here for all x and y, P of x and y. That's for all x. So it's more on the commutative laws. Gibaylo lang si x o si y the same on the above form. Next we have for all x, P of x and Q of x is simply equivalent to for all x, P of x and for all x, Q of x. So we have distributed for all x to P of x. This is the answer. Copy the collective and we have for all x distributed to Q of x. This gives us for all x, Q of x. Next, we have in here, there exists x, P of x or Q of x. So the same law that we had, distribution. There exists P of x. So we have there exists P of x, or for some x, P of x. Copy the logical connectives and we distribute again for some x, Q of x. We have the negation example. We have not the negation or not, let's say the negation for all x, P of x that is simply the same or equivalent to there exists x, not P of x. For example, your P of x is given by the statement x is a student of CSE, where the universal discourse is the students of this class. So your statement for all x, P of x will be all students in this class is a student of CSC. The negation will be in this form, or in English statement that's just not every student in this class is a student of CSC. And it is just the same with this form, or in English statement there is a student X who is not a student of CSC.